Thanks a lot, Blake. Thanks, Michael. Thanks, Amrit, and thanks the rest of the team for running this. It is really quite a treasure trove by now on YouTube. I think we are it's pushing 50 talks or something like that. I would encourage everybody to go there and take a look. There are some excellent ones there. Okay, so Amrit asked me to deliver an extended version of the lecture that was given at the Ampere School in virtual Zakopane this year. And it is a tutorial talk. It is the briefest of introductions into the nuclear structure theory, but it is geared for chemists and biologists and mass spectroscopists in particular, because they always have, every time we teach these deep topics, this question of, well, okay, but what is magnetogyric ratio? What goes on inside the nucleus? How come nuclei can have such a great variety of magnetic moments and spins? And what is nuclear spin to begin with? And why is an electrical interaction, such as nuclear quadrupolar interaction, suddenly become magnetic and influence spin? And why on Earth would the direction of electric quadrupole follow the direction of the magnetic moment vector? And such other things. So the fundamental question that is rarely addressed in chemistry departments, certainly isn't addressed in any of the mainstream magnetic resonance textbooks, is what goes on inside the nucleus. How does the nuclear magnetogyric ratio appear? How can it possibly be negative? Because it's classically impossible for a positively charged particle to have a negative magnetogyric ratio, but apparently such particles exist, and so on and so forth. So we will be looking today into inside the nucleus to find out what is going on there. But first, to whet your appetite a little bit, let me outline, the outside picture of what we are looking at. Nuclear structure is an enormous topic with Nobel Prizes and huge books written about it and databases of nuclear densities and such like. There's a good example here. Of course, chemists like ourselves, we used to treat the nucleus as a point charge, right, somewhere within the molecule, just a Coulomb interaction, but of course it very much isn't. It has a finite spatial extent, a few femtometers, and in fact its surface is diffuse. So this is from the nuclear charge density archive, where the charge density has been measured by scattering experiments. And you can see, so yellow's carbon-12 and 40 is calcium-40, the blue's calcium-40, this is lead. And you can see that the charge density falls off fairly smoothly, first of all, so the surface is diffuse. But also there are these interesting dips at the center, right? So carbon-12 is apparently slightly more dense on the outside than it is on the inside, and we will see why in a few moments. Then nuclei come in a variety of shapes. You knew it already, but actually the shapes are very rich, quite extraordinary. You can have things that are egg-shaped, things that are mango-shaped, and certain vibrational excitations, and there are such things as vibrational excitations of nuclear structure. They're actually heart-shaped nuclei. And then a nucleus can be spun up and down by irradiating it with gamma rays and X-rays. This is a very famous case of erbium from this review, where, of course, the ground state of the nucleus has a moderate spin. But if you start irradiating it with gamma rays of sufficient energy, you can start spinning it up. Or if you have an off-center collision in a particle collision experiment, that would also impart large angular momentum on it. And as you start spinning it up, you can see that the nuclear spin can be pumped all the way, into 50s. So nuclear spin, 99 halves is actually realistically achievable and measurable in the excited states of some nuclei. And as you start spinning it up by this irradiation or collisions, you would have shape changes, right? So previously prolate nucleus would turn oblate if you spin it up sufficiently. At some point, as you start spinning it up, valence neutrons, the unpaired neutrons, would align themselves to the axis of rotation. And then the protons would align themselves in the axis of rotation. And then at some point, what happens is the valence nucleons, the ones that do not belong to a magic number core, they stop transforming by the spherical group and start transforming by cylindrical group. And this review paper actually compares the resulting nuclear structure to the rings on Saturn, in that these nucleons are orbiting the rigid core of that nucleus. And sooner or later, as you keep spinning it up and up and up, past spin 70, the whole thing flies apart because you've spun it up so much that you've destabilized it into strongly triaxial deformations, and then there's just a splitting. So this is what you can do to the nuclei that are never mentioned in any of the magnetic resonance textbooks. And it's not just the excited states. Nuclear ground states can look pretty weird. That's samarium, that's tungsten, that's lead, ever so slightly non-spherical. That's platinum 190. And all of this and the associated theory and the associated mathematics is actually 1975 Nobel Prize by the son of Niels Bohr in particular. And we will now go not terribly deeply, as deeply as we can in 45 minutes, into why all of this happens and how the nuclear magnetic moment comes to be. But what I must do before that is I must remind you, because you're all chemists and biologists, I must remind you how we treated the electron in the hydrogen atom, because we will borrow a lot of that mathematics now. Remember how we did it, right? So the energy of a particle, in the case of hydrogen, of the nucleus and the electron, is just the sum of the kinetic energy and the potential energy. And the kinetic energy is this momentum, p squared is the Laplace operator, second derivative, for the nucleus, the same term for the electron, and then the electron-nuclear Coulomb interaction, just a straight Coulomb interaction of the two charges. And as we all did in our second year when we studied molecular quantum mechanics and we did the hydrogen atom structure, we transformed it into the center of mass frame, at which point we don't care about the whole particle moving as a whole somewhere, we're only caring about the relative motion. And then you have the momentum term for the effective reduced mass. And you've got the nucleus, roughly speaking, in the center in the Born-Oppenheimer approximation. And then that's just the electron position, because we position the nucleus in the center. And when we did that, remember the next steps that we took, the steps that got us the atomic orbitals. We did the variable separation. We realized that this potential is centrally symmetric, and so the radial coordinate is independent from the angular coordinate. We can split them up. And so we said, well, okay, let's look for our atom orbitals, so orbitals of the electron in that atom, as radial part times angular part. And after a horrendous pile of mathematics that I still have painful memories of all these years later, it separates into a radial part, which is system specific. It's different in each atom because the different number of electrons and so on. But also the angular part, which is universal because every single atom has complete spherical symmetry. And so the radial part was complicated and horrendous and difficult to deal with, but the angular part was the same, or essentially the same, in every non-relativistic atom. And that had solutions, and that gave us the principal quantum number, and that had solutions, and that got us the orbital and the magnetic quantum number. And those were our atomic orbitals in the hydrogen, and this was the standard orbital classification. If you remember, we had 1, 2, 3, 4, 5. Those were radial quantum numbers. And then we had L and M, and those were responsible for which orbitals we have, S, P, D, F, and so on. And then for the projection inside those orbitals, we had 3 projections for P's, 5 projections for D's, and so on. And notice the important thing here. The radial part does depend on the system. If we now go inside the nucleus, the radial part's probably going to be different. But the angular part is universal because the angular part is common to every particle that has a spherical symmetry. And so we would probably be able to inherit this. So let us now abandon this flashback and now go inside the nucleus. What about the strong nuclear force? which keeps the nucleus together? Well, firstly, it's a very different range. Coulomb interaction was, angstroms and such. Strong nuclear force is 5 orders of magnitude shorter in the distances that you realistically encounter. It's around a femtometer. Its amplitude is about 100 times stronger than the electromagnetic interactions. You will see that in our case now, electromagnetic couplings will just be perturbations. It has a complicated origin. It's a residuum of the strong force between the quarks. Very roughly speaking, I'm simplifying here, it bears the same relationship to the strong force that keeps the nucleons together, so that binds the quarks, as the van der Waals interaction bears to the Coulomb interaction. So it's like it's a perturbative residuum of the strong force that binds the quarks. Its potential is unknown. We can hack together from symmetry considerations its generic form, but the various coefficients and gauges in there are unknown. It might not exist to begin with because it's an effective quantity, but we know for a fact that it's pretty likely to be centrally symmetric. And in fact, these models tend to agree with reality quite well. Okay, what can we think about? Well, of course, quantum mechanics in some sense is scale invariant. And so we expect a single nucleon Schrödinger's equation to also have a kinetic energy term and the potential energy term, whereas the kinetic energy, it follows from basic symmetries of space-time. Actually, we had a lecture on this when we discussed the nature of spin a few months ago. If you Google it up, you'll find it. So this has to be universal, but of course, there's some kind of center symmetric, hopefully, potential that we don't know about and probably never will. So we will have to approximate it with something. Okay, but of course, if we were to do it like that, then we inherit the variable separation process. There will be the radial part, which contains an unknown term here, but there will also be the angular part, which is exactly the same as what we had for the hydrogen atom. So we expect to find the same SPDF and so on classification for the nuclear orbitals as we had in the hydrogen atom. Okay, so what's the strategy? Well, we don't know what this potential is. Why don't we postulate something, harmonic oscillator, infinite square well, something like that. And then we will tweak that potential until the magic numbers are reproduced. And these magic numbers correspond to the nucleon counts in particularly stable nuclei. So I'm retracing the history here. So at the moment, we are roughly in 1930s to 1940s, when all of this logic was going through people's heads. And it turns out that in this non-relativistic, non-quantum field theoretic description, a pretty decent potential that tends to reproduce all of these magic numbers, the energies, the angular momenta, and other things to pretty decent accuracy, all the way, to argon or thereabouts. Is this Woods-Saxon potential, and that is essentially a square well with slightly rounded edges. So that would be the retention potential, just some empirical mean field retaining force. And then we would have some Coulomb interaction between the protons here. And of course, that means we would have two different potentials. One retaining potential for neutrons, which do not have Coulomb interactions with protons or between themselves. And there will be a separate potential slightly higher up because of Coulomb repulsion for the protons and their Coulomb repulsion. But essentially, mathematically, for the radial part, we are different. But for the angular part, we are exactly the same as we had for the hydrogen atom. Okay, so let us solve that and take a look. If we put the radial part to be a harmonic oscillator, of course, it's nowhere near the experiment. It's horrendous, it's completely broken, it doesn't match. So people abandon that. The next best thing we can try is an infinite square well. It gets ever so slightly better. Then finite square well, even better. And when we go to Woods-Saxon potential, it's actually pretty decent in that you start reproducing some of the magic numbers, but not all. Now, the nuclear physicists have messed this up a little bit relative to what we have in chemistry. In chemistry, remember, we had a principal quantum number classification, and then inside each principal quantum number, we had the orbital quantum numbers, and everything was nicely ordered. I fear that the nuclear structure people have made a bit of a mess out of it. They have renumbered their orbitals in a way that essentially they just number them in the order of appearance. So the first s orbital is called 1s, the first d orbital is called 1d. It might actually come from the second principal quantum number. It is still called 1d because that's the first time this d orbital occurs, and so on, 2s and so on. So they are numbered not in the way that chemists would expect them, numbered in the order of appearance. The other difference from us, from the Coulomb interaction as a potential, is the nuclear structure people have pretty high angular quantum numbers. We never actually see H or I orbitals, unless we go to Rydberg atoms or something like that. But in nuclear structure, these occur pretty early on and are actually populated and are important. And the last difference from the hydrogen atom, of course, these energy gaps are all in the hundreds of kiloelectron volts and mega electron volts. At room temperature for any realistic chemical system, we are absolutely in the ground state of this structure, right? Unlike, for example, transition metals that we have in electronic structure theory. Okay, so I've done a little bit of a calculation using spinach because there's plenty of partial derivatives infrastructure in there. That's the Woods-Saxon potential in 3 dimensions for the charge 20. I've made that Woods-Saxon Hamiltonian, resolves momentum terms, diagonalized it, and plotted the eigenfunctions. So as you can see, the first eigenfunction is S-type, so it is spherical, but you can see the edges are rather diffuse. Then if we go to second eigenvalue, all right, so that's a p-type orbital, and there are 3 of them here, so you can see the p-type density that is condensed inside that smoothed square well. And that's the eigenvector 5, which would be one of these d-type orbitals, and you can see d-type density. So actually, from the angular point of view, the classification is almost identically the same as the hydrogen atom, but of course the radial part is different, and so we've got a different energy ordering in here. If you're interested, get the latest development version. So far it is of spinach, and this example that generates these nuclear orbitals is there. Okay, so we've kind of got a little bit of a hang, right, of how the nucleus is organized inside. It's a different energy order, but substantially the same orbital classification as what we had for the hydrogen atom. At this point, I need to give you another flashback, right? So we leave the nucleus to the side and we go back to the electronic structure theory, which we know and love. Remember how we classified the states of all of those transition metals? You know, like copper and iron and so on. We had a pretty significant interaction there called the spin-orbit coupling. And that is from special relativity. It falls out of Dirac's equation when you eliminate the negative energy subspace. But essentially, it's a scalar coupling between the spin and the orbital angular momentum of a particle in a Coulomb potential. Notice here that the electron is negatively charged, so this Q is negative. And there's a minus here, so this quantity is positive. And so what it means is that the orientations of spin and orbital angular momentum, the parallel orientations, are higher in energy than the anti-parallel one. And that creates a particular electronic structure. And what is important here is that this SL has some very nice commutation relations. It commutes with the total momentum, total angular momentum. It commutes with total spin. And it also commutes with the sum of the orbital angular momentum and spin. And remember this nice mathematical fact. If the 2 operators commute, they share the same eigenfunctions, right? The eigenfunctions. The eigenvalues can be different, of course, but the eigenfunctions are the same. And so we can classify our states by the eigenvalues then, right? So eigenfunctions are the same, eigenvalues are different, eigenvalues can be used for classification. And this is the origin of those term symbols, right? L is the good quantum number, S is the good quantum number, the total momentum, this is called J, is the good quantum number. And so our term symbols in electronic structure theory had spin here, 2s+1 for historical reasons. We had L here, SPDF, and so on. And we had J, this L plus S in there. And this is how we classified our terms. And this is because this SL commutes with the J. And then when we do the actual diagonalization, we get these energies. Turns out that these states are degenerate because they're also projection, and they're called multiplets. And this is what these were. And in any electronic structure textbook, you will remember that there was this electronic configuration that came out of the Coulomb interaction with the nucleus. Then the Coulomb interaction between the electrons split it into terms. So inter-electron repulsion gets you terms. Then this spin-orbit coupling splits those terms into multiplets. And remember what I told you about this being positive. The largest total momentum is at the top because parallel orientations of S and L are higher in energy than antiparallel. So the highest momentums here. And then, of course, all of these multiplets, individual projections of the momentum, would correspond to individual little orbitals like px, py, pz. And they are differently spatially oriented, right? And if you put around a few charges, like you put a ligand in there, you would split those magnetic sublevels. And essentially what happens is different projections of the total momentum have different energies. The result is an operator that effectively acts on the momentum, and it's called the zero field splitting. So parallel orientations are higher in energy, and the zero field splitting essentially says that the states with different M have different charge distribution and therefore different energies. So this was the hydrogen atom. And look at this. This entire classification is based just on spherical symmetry and spin. And so the wonderful thing about nuclear structure theory is because this is all spherical symmetry and spin, this translates exactly into the classification of spin-orbit coupled multiplets inside the nucleus. Okay, so now we go away from the electrons and we return to our task at hand. We return to the nuclear structure. Okay, so this is our square well with rounded edges, and these SP, DF, and so on are the functions of spherical symmetry and of the Wood-Saxon radial potentials that we have. And now we introduce the spin-orbit coupling. And the spin-orbit coupling is now going to be different. Remember, that was the derivative of the radial potential. And our radial potential is non-decreasing. It keeps increasing, sometimes faster, sometimes slower, but it keeps increasing. So this is a positive number. All right, there is this still minus in front. So overall, this is negative. And so the spin-orbit coupling in the nuclei works in the opposite way compared to how we did in the electronic structure theory. That is, the highest momentum level is at the bottom, not at the top, right? So spin and orbital quantum numbers always couple for the maximum total momentum, not the minimum, like it happened in the hydrogen atom. So parallel LNS orientations inside the nucleus are lower in energy than the antiparallel one. Okay, it's the same story. SL commutes with the total momentum. We can build that operator. We can diagonalize it. We get these energies that are functions of the J, L, and S. These are good quantum numbers. They enumerate our multiplets. And behold, we have this spin-orbit splitting, where now these are again the numbers in the order of appearance. That is the orbital quantum number, L, so SPD and so on. And this is the total momentum, J. And as you can see, the largest J is now at the bottom. And you have two instances of this picture, right? Protons in between themselves are constrained by the Pauli exclusion principle. So at most 2 protons per level then. Neutrons individually between themselves are constrained, so at most 2 neutrons per level, but protons and neutrons are individually distinct. And so they are not between themselves related by a Pauli exclusion. So you have effectively an independent system of levels for protons and an independent system of level for neutrons. And we will now start occupying that. And of course, this resulting energy level filling order predicts the magic numbers, and that was that 1975 Nobel Prize in particular. Okay, so let us start populating these energy levels. Let us look at nuclear structure configurations in the same way as you may remember from your second year as undergraduates, we were doing electronic structure configurations. Okay, so carbon 13. Remember the 1s½ level. So 2 protons go into there, 1 spin up, 1 spin down, but also 2 neutrons into the other level system. Then we've got 4 protons in the p3½ orbitals, and we've got the 4 neutrons in the p3½ orbitals as well. But we have 1 unpaired neutron. And this 1 unpaired neutron has to go into the 3rd orbital in this structure, remember 1p1², and the total angular momentum there is 1/2, so that is the total between the orbital and the spin. And so we have the total momentum of 1/2, and that is the spin of the nucleus. Notice that the word spin here is in the inverted quotes. Nuclear spin isn't actually spin. Nuclear spin is the total angular momentum of the ground state. If you look at, for example, nitrogen 14, same story. So you have an extra proton there, but you also have 2 extra neutrons. And so N15, you have paired neutrons, so no total momentum. And you've got an unpaired proton, so again, J½ But if we look at something a bit more interesting here, if we look at oxygen 17, it has fully filled 1s², fully filled 1p3², fully filled 1p1². So we have 1 unpaired neutron in d5². So the total J is 5², and this is why oxygen 17 has spin 5². And this, of course, actually mostly isn't even spin, right? Out of this 5², only 1/2 comes out of spin, and it's the L equals 2 d orbital that produces most of the angular momentum of the oxygen 17. So it's not actually just spin. Not only is it not just spin, it's actually mostly orbital, right? So what you have here in oxygen 17, and that's the occupation diagram. So these are the proton energy levels. See, there's ever so slightly higher in energy because of the Coulomb repulsion. And these are the neutron levels, and you have this single unpaired neutron kicking about in d5². And this is why you have the total, what we chemists call spin 5½ for the oxygen. Nitrogen 14, you have 2 unpaired particles, 1 proton, 1 neutron. In that case, they couple for the maximum total momentum, so you do have an effective eventual spin 1. And in situations like oxygen 16, fully occupied nuclear configuration shell, everything's paired up. And so here you've got the total spin 0. And this is how nuclear spin comes about. Okay, so now we need to go slightly deeper. Okay, we figured out more or less where nuclear spin's coming from. Now we need to figure out where the nuclear angular momentum's coming from. Sorry, not momentum, the magnetic moment. And this, in fact, is surprisingly similar to how G factor turns up in EPR spectroscopy. So if there are EPR spectroscopists present in the audience, you would actually recognize the picture now. So remember what we had in our nucleus. I told you that those gaps between energy levels, and in fact, more generally, the gap to the nearest excited state, is usually in the kilo-electron volts at least. There are a couple of rarest exceptions. There are a few exotic nuclei where the excited states are just a few electron volts away, but that's vanishingly rare. Certainly not for light elements. The nearest excitation is like 100 kilo-electron volts. And so at room temperature, we are very much in the ground state. And so what we now need to do is we have to project our entire dynamics and all the operators we have into the ground state multiplet. So we've got these nearly degenerate magnetic sublevels of our J multiplet, and we've got some monstrous excited states somewhere. So what we must do is we must identify this block of the Hamiltonian at the very bottom that's responsible for that. We must take whatever operators we are interested in, and we must project it into the subspace that is spanned by these things. So for any vector operator, for example, magnetic moment, in a specific J multiplet, well, there are two ways of doing it. One is the complicated one that I will briefly describe, and then there is a more intuitive, simpler explanation, which unfortunately then involves a slightly generalized group theory. So it's complicated either way, so I thought that I'd give you both explanations there. So Wigner-Eckart's theorem says that if you have a certain operator, that the matrix element in any J multiplet is actually a multiple of J itself. Now, this isn't obvious why that should be the case, and the explanation, in fact, comes from group theory. So here you have these energy sublevels. They correspond to a particular J multiplet, which is a particular irreducible representation of the rotation group. In this case, something slightly more complicated. It's SUN, but a particularly irreducible representation of a certain unitary group. And then it has its associated algebra. And if you project any operator into that algebra, the only thing you can get is a linear combination of generators of that algebra. And in this case, it's basically just J. So you have this matrix element, which is just a number. And you've got this matrix element. And so in essence, for rank 1 vector operators, what this theorem tells us is that matrix elements of any operator are related to matrix elements of the total momentum. And this is how a magnetic moment ultimately becomes connected to spin. So let's go in slightly more details into that. So we've got this J multiplet subspace, right? A few nearly degenerate levels. We've got, therefore, in the Hamiltonian, a J multiplet block. So we must project A into the current J multiplet subspace. That is the mathematical formulation of that, rigorously derived. My sort of hand-wavy picture of that, you have to know a little bit of the algebras for that. But if we project anything into an algebra, we inevitably get a linear combinations of the generators of that algebra. And if the algebra in question is the algebra of angular momentum, then we get an angular momentum operator. Remember that for nuclei, this is what it's called spin. And so this is how anything becomes a spin operator, ultimately. Okay, so flashback. Back to the electronic structure theory. How did we get G factor and how did we get zero field splitting for some, transition metal, electronic structure theory? Remember what we had there. We had the magnetic moment, which was Bohr magneton, and it had the orbital contribution and it had the spin contribution, but we were sitting in a specific multiplet. In fact, in electronic structure theory, sometimes we don't, but in the simple cases, we do. So we use that Wigner-Eckert theorem to project into the ground J multiplet. We've got this as a good quantum number and that and that. So we classify it by those quantum numbers. That is that prefactor from the previous slide, mu dot J, where A had been. So we substitute mu and put it into there. J is a good quantum number for all of these operators. It's an eigenfunction for all of them. So we get a bunch of eigenvalues in here. And this horrible crocodile is known in the trade as Landay's G factor. Comes out of the J multiplet projection of the magnetic moment operator, and then it becomes proportional to the total momentum operator, and that was the reason why. Right? We have projected an operator into a specific algebra. Now it must be a combination of the generators of that algebra. And likewise for zero field splitting, right? You got ligand field electrostatics. They get some electrostatic operators. Through the Wigner-Eckert theorem becomes an effective spin operator. So this Wigner-Eckert theorem essentially turns anything that acts onto JM operators into an effective spin interaction. So now our mission is to do exactly the same, but for the nucleus. Okay, so what about the nuclear magnetic moment? It's ever so slightly more complicated. Now it's not Bohr magneton. This is now a nuclear magneton, EH over 2 proton masses. And remember, for electrons, the orbital G factor was exactly 1. The spin G factor was 2 point blah, blah, blah. Now we don't have electrons. Now we have protons and neutrons. And for proton, of course, the charge is +1, so it's exactly 1. For a neutron, the charge is 0, so it's exactly 0. The funny thing comes from these spin G factors. And this is actually another level of complexity. Everything that I just told you about nuclear structures here also applies to the nucleons, because they are also the ground state of a system of 3 quarks. And those 3 quarks have got their own spin and their own orbital angular momentum. So actually the spin G factor of proton and neutron are also effective quantities that come out of the quantum chromodynamics of the effective structure of the proton and the neutron. So I will not tell you where these come from, but look at this negative sign in here, right? So neutron spin G factor is negative. And this is why nuclei can have negative magnetogyric ratio. Remember, we had some unpaired neutrons in some of those nuclei that we have considered. So this explains nuclei with negative magnetogyric ratios like nitrogen 15. Okay, so at room temperature, I remind you, we are very much in the ground state of the spin-orbit coupling operator, because the nearest excitation is 100 kilo-electron-volts away. So again, it's a J multiplet. Again, we must project into it. Again, we have this mu and mu dot J, so it's exactly the same Wigner-Eckert theorem. And after we substitute mu, see, this is a bit more complicated now. It's not just 1 and 2, right? We've got actual factors. After we work through the matrix elements in here, we get this horrendous matrix element, and that's the proportionality coefficient between the magnetic moment and what is now nuclear spin, and this is the magnetogyric ratio. And this is where it comes from the ground multiplet projection of the full magnetic operator. Notice that this is only the case when we are in the ground nuclear state. If we consider nuclear dynamics, if we have just smacked that nucleus with a gamma ray and it's really evolving in time, then the nuclear magnetic moment is not proportional to the total momentum. It's not proportional to the orbital momentum. It's not proportional to spin. It's not proportional to their sum. It is something else entirely, right? Magnetic moment only becomes proportional to spin when we drop into the ground state multiplet of the nucleus. Okay, so for us chemists, mu is then gamma J. This is only simple for single unpaired nucleons. If you've got multiple unpaired nucleons, this mathematics becomes horrendous, but this final result survives, that magnetic moment is a multiple of the nuclear total momentum, which we chemists call nuclear spin. It's qualitative treatment, this one. Of course, there are a lot more interactions and perturbations, like Coulomb interaction, for example, between the protons, which we didn't even consider here. So other contributions to gamma also exist. So this treatment is qualitative in the same sense as lambda G factor, right? It's a sketch after a while. Okay, so we more or less, I think, figured out where the magnetic moment's coming from. Let us now take a look at the electric quadrupole, and by what kind of bizarre twist of physics it ends up being a spin operator, because of course it's pure electrostatics right on the surface. I will remind you the multipoles. We've got electric dipoles, quadrupoles, octupoles, and so on. We've got magnetic dipoles, quadrupoles, and so on. And there are actually, in this wonderful paper by Nikitas Papasimakis, who's just next door here in the physics department, there are also toroidal multipoles. There is a less known third type of multipoles, but I digress. So let us go into the Taylor expansion for the electrostatic potential. You just standard Taylor expansion. Multivariate, so zero order term derivative times r, second derivatives times r and r, and we can reorder it a little bit. It's a trace of that, and this is a second derivative matrix. And remember Laplace's law, the Laplacian of the electrostatic potential is equal to the charge density. In most places it's 0, so this is traceless by Laplace's law. And so we can then separate the total energy of a charge system in an electrostatic potential into the Coulomb contribution, just charge, dipole contribution, quadrupole contribution, and so on, where we have the total charge, which is an integral over the charge density. we've got the total dipole moment, which is the first moment of this distribution. We have the quadrupole moment, which is the second moment of that thing, deliberately made traceless here. And that's just a standard multipolar expansion in physics. Now, what is important is nuclear dipole moment in the vast majority of cases. You really have to go general relativistic before this breaks. But in the vast majority of cases, because our wave functions are parity eigenfunctions, they are either invariant or they change sign under inversion. Necessarily, the absolute square of that is invariant under coordinate inversion, so there cannot be a dipole moment. Right, it is symmetric with respect to inversions of charge distribution. So nuclear dipole moment must be 0. So the first electric multipole that we're going to have is the quadrupole. And then it's actually quite easy to make an operator out of it, right? We've already made it, right? It's just a bunch of coordinates. So that's our electric quadrupole operator. And the quadrupoles interact with electric field gradients. Remember that the first derivative of this is the electric field. So the second derivative is going to be the electric field gradient, and everything's simple, except of course for one thing. These are purely coordinate operators. They have nothing to do with spin, nothing whatsoever at this point, at least. But of course, the same factor kicks in. Remember, we are in the ground multiplet of J squared, and remember what I told you about that projection. The moment you project anything into an algebra, you get a linear combination of the generators of that algebra. And if in our case, this is SUN of the ground state multiplet of J squared, you will have to have SUN generators, basically spin operators for our purposes. Okay, so the same old story, same J multiplet subspace, the same block, the same projection, except we are now projecting the quadrupole operators. Now, in this case, the Wigner-Eckert theorem becomes a disaster. You have to make second-rank irreducible spherical tensors and spherical harmonics in this case. After the projection, they become irreducible spherical tensor operators. You don't want to know. Trust me, it is a disaster. A much simpler approach is, in fact, to observe that our total wave function must be, right, it's a general theorem in mathematics, it must be a linear combination of Kronecker products of all the spatial basis set and all the angular momentum basis set, right? So we are sitting in a state with a defined J, so we will have projection quantum numbers here, and they will have the corresponding spatial contributions, and the general wave function is a linear combination of those. And so once we take that and take matrix elements of that, of those operators, you will see in a moment, we will get a nuclear spin operator. Okay, let's do it. So we are in the ground multiplet of J squared. So we've got this, we've got some spatial part, and we've got the spin part. The space part is in the ground state, and the spin part is dynamic. For the Hamiltonian, necessarily, we have direct products of spatial blocks and the spin blocks, and it's a linear combination of them. And then if we were to take the matrix element of that, we split it into the integrals with respect to space and the integrals with respect to spin, which are just, in this case, Kronecker symbols. And so after the dust settles, we have effectively a spin interaction, because all these spatial integrals are just constants, right, depending on the system. Another way of looking at it is we've got NJM quantum numbers, where N and J are fixed by our ground state, right? And therefore, effectively, this is just M and M prime. And so effectively, it's with respect to the projection of the angular momentum, which we chemists call spin, and therefore, that's effectively a spin operator. So I've skipped maybe a couple of pages of really dense mathematics here, but after the dust has settled, you get our lovely quadrupole Hamiltonian, which we all know from the standard textbooks. You have the quadrupole constant, you get a bunch of normalization operators, and these are our nuclear spin operators, and this is the electric field gradient. And of course, our usual parameterization. We have the quadrupolar coupling constant, something that's experimentally measured, and the asymmetry of the electric field gradient in this case. So the basic explanation for this is every nuclear spin state is connected to a particular spatial wave function. They're different. They interact with electric fields. And so that splits our nuclear spin sublevels. And therefore, what started its life as an electrostatic interaction, effectively as you know, a twist of all this mathematics, becomes in the end a spin interaction. So, okay, to summarize, what goes on inside the nucleus? Well, the potential for the strong nuclear force is basically unknown and probably will never be. Quantum chromodynamics calculations are horrendously complicated, not anytime soon. Spin-orbit coupling in the nuclei is stronger than Coulomb interaction, and so it dominates the orbital classification. Nuclear spin isn't actually spin, it's the total nuclear angular momentum. And we as chemists at room temperature are, of course, always in the ground J multiplet of the nuclear structure. And so the first corollary is the magnetic moment becomes proportional to the nuclear spin operator. And the second corollary is the quadrupolar interaction also effectively becomes a spin operator for our purposes. And I would encourage you to do quite a little bit of further reading on this. The quadrupolar NMR is introduced very nicely by Pascal Mann in the NMR encyclopedia. Probably the most beautiful application was invented by Lucio Friedman and company. So this is their original MQ-MAS paper. And all in quadrupolar NMR, you can have overtone transitions, so you can skip a level. And that is the original paper, I think, from Stenapella on the subject. Nuclear quadrupole coupling is strong enough to compete with Zeeman interaction, and so you can do it in the absence of the magnet. This, I think, is a paper from Dima Butker's group on the subject. You can have multiple angle rotation to get rid of the quadrupolar Hamiltonians. This, I think, is instrumental paper from Aga Samason and company. Aga's making beautiful double rotation probes that then allow you to characterize those interactions in depth. This is the nuclear shapes paper that this Mango came from. And these are the two Nobel Prize winners from 1975 that got their prizes for explaining everything that I've just explained to you. And if you want to read the story in a bit more detail and in a way that is adapted to NMR spectroscopists, I should be able to finish my book by about Christmas. So on Christmas, it goes to the publisher. At some point will come out. And this, in fact, is a visual and graphical summary of one of the chapters in that book. So please get it as soon as it's out. I don't honestly know how long it would take Springer to process it, but I'm working on it. Okay, and thank you for your attention.
Thank you very much, Ilya. That was incredibly informative. And it was great to see all of this presented so clearly and in a way that I've never seen laid out quite that way before. So thank you.
Okay, so we got some Q&A, I think.
Yes. Why don't we start with the question from David Bryce in the Q&A. David asks, in your example calculating the spin of carbon-13, for example, it seems that the spins of the two protons in the first 1/2 level cancel each other. Sorry, in the 1s 1/2 level cancel each other, resulting in 0 for that level. But I thought you said that both protons up is the lowest energy configuration.
David,
add to a total spin 1.
This is for the unpaired ones. So imagine that you've got only one level and the nearest excitation is pretty far. Of course, if you have two particles in there, then they've got the choice of becoming anti-parallel by the Pauli exclusion principle, or have a 10 kilo-electron-volt excitation. So this pairing interaction is weaker than the nearest excitation. And so if you have two unpaired nucleons in different orbitals, they will pair up for maximum spin. But if you have two unpaired nucleons forced to coexist in the same orbital, they will become anti-parallel. And this is why you only have one unpaired nucleon in that structure.
Great.
Does that answer the question? I think, David, can you go visual?
David says thanks. Great. So let's see. We have a question from Andre. Why is nitrogen-14 spin 1, not 0?
Because of exactly the same answer that I just gave to David. There you have two orbitals. So there is no Fermi exclusion principle constraint. And when you have that, then the nucleons do couple for the maximum spin.
Great. So here's a question from Eric that I think is a good thing to address. Eric asks, is there a simple explanation of why the nuclear dipole, I assume he means nuclear electric dipole moment, must be 0?
Oh yeah, of course. I mean, so basically all the nuclear wave functions must be parity eigenfunctions. So if you perform coordinate inversion, the psi can only become plus psi or minus psi, right? And so when you calculate the density, density is psi absolute square. And so because of that, the density is constrained to be invariant under coordinate inversion. And for any function that's invariant under the coordinate inversion, the first moments vanish. And so mathematically, the electric dipole must be 0.
Great, thank you. We have another question from Andre. He asks, can you repeat why the nucleon potential is non-decaying?
It's just monotonic. I mean, remember how it looks. It's level floor, then it goes a little bit up, and then it rounds off and keeps going. So if you trace it from R0 to R infinity, it never actually decays. And so derivative is always non-negative, and that's it.
Great. All right, we have a question from Mohammed Saba. He asks, you mentioned quantum chromodynamics and 3 quarks. What is your personal opinion on the nucleon spin crisis of QCD?
Oh, I don't know enough about it to have an opinion. So here I must plead ignorance. So I haven't looked deeply enough to even know what it is. Sorry.
Great, maybe.
Right, who's next?
Great. So let's see. We have a question from an anonymous attendee. Will your book also discuss the origin of specific low and high gamma nuclei? For example, is it easy to show why fluorine and phosphorus must be high gamma?
No, it's only very qualitative, right? So it goes far enough to explain people in general outlines where nuclear spins coming from, but of course this is not a textbook on nuclear structures. So I very specifically stop on systems with a single unpaired nucleon.
Eddie asks, dear Professor Kuprov, thanks for the interesting talk. I don't know if my question is correct and connected to the talk today. I can understand that protons and neutrons are quarks associated differently and they have different charges with the same mass. Electrons are different. Why do they have the same absolute charge as protons?
I guess nobody knows is the answer to that. That appears to be how the universe works. I think if you ask why the fundamental calibration constants of physical theories have the values that they have, the honest answer is nobody knows.
We have another question.
From Andre, right? Is J half a problem for Q? Yes, it vanishes. Yeah, I mean, it's actually quite easy to demonstrate. If you look at the squares of spin half Pauli matrices, so remember we necessarily had squares of the generators. The squares of Pauli matrices for spin half are all multiples of the unit matrix. So the whole thing collapses. It's mathematically a projection from SU3 down into SU2. So SU3 has 8 generators, the 3 Zeeman operators and the 5 quadrupole operators. All right, so a 3-level system can support a Wigner-Eckert projection of the quadrupole, but SU2 cannot. So essentially, the algebraic form of that operator collapses into a unit matrix.
Thank you. One more question from Eric. He asks, why is mu not proportional to J in the nuclear excited state?
That's a loaded question, right? In any excited state that is still itself a multiplet, right? So if you are considering an excited multiplet of the total momentum, then it will be. But of course, an arbitrary nuclear excitation might engage multiple multiplets. And in the same sense that in strongly excited states of transition metal complexes, there is no such thing as a G-tensor, right? There will be no such thing as a magnetogyric ratio in a mixed nuclear state. So we rely, so long as we require the wave function to be a pure state with respect to the spin-orbit coupling, mu will always be proportional to J. But as soon as it isn't, the proportionality breaks.
Great. So here we have a question from Jamal. We just have a few more questions. This one, Jamal asks, this question is a bit far from the main topic, but if I may ask, it's about the invisibility of multiple quantum coherence in Fourier transform NMR. I know that it is directly visible in CW NMR. Why not in FT NMR? Is there an intuitive explanation?
Actually, they're not, strictly speaking, directly visible in CW NMR. In CW NMR, you simply see forbidden transitions, right? So all of these single quantum, multi-quantum, and so on classification, remember that these are the eigenstates of Zeeman operators, right? So the quantumness, zero quantum, single quantum, double quantum, is determined by the commutator with LZ, right? If you have a single quantum state, LZ commutator L plus is L plus. If you have a double quantum state, LZ commutator L plus squared is 2L plus squared. So the assignment, zero quantum, single quantum, double quantum, is an eigenfunction of the Zeeman operator. So strictly speaking, this classification only applies in the high field limit. As soon as your interaction is very strong, like quadrupolar interactions and so on, the LZ is no longer the dominant coupling. You start having perturbative admixtures of everything else, and various other states become perturbatively allowed. So what you are still seeing in CW NMR, strictly speaking, is a transition with respect to Lx. It's a matrix element of Lx. But it's a matrix element of Lx between the states that have been mixed away from the Zeeman eigenstates by the quadrupole coupling. So they are not multiple quantum transitions. They're only multiple quantum transitions with respect to the LZ basis. They are still, well, that's I guess, as close to it as I can express. So I would say the real reason why there's a difference is that we are detecting slightly different things in CW versus time domain. In the time domain, that's just the time dynamics, but in the CW, there's a so-called eigenfields, right? So this is match between any two energy levels and the current radio frequency or microwave, which could be between states that have been significantly mixed away from Zeeman eigenstates.
Great, thank you. I think that says it pretty clearly. Only a few questions left. We have a couple of questions about your book. Mohammed Sab asks, when can we get your book? And in the chat, Jeffrey Reimer
can have it tomorrow because you are just next door. So if you promise me that you will find all the minus signs for me and all the bugs and all the typos, you can read it tomorrow. In the actual press, that depends on how fast Springer is. I will send it to them straight after Christmas, and then it's in their hands. I don't know.
So we also had a question from Jeffrey Reimer asking who is publishing the book, but you just answered that as well. Great. So there's one more question in the Q&A from Giuseppe. Giuseppe asks, to get the proton spin, I guess one has to repeat what you did, but on the quarks that have their spin in orbital angular momentum. So the spin of the proton should come out of such a calculation. According to what I know, this is not yet sorted out. Is this true? And I think this comes back to the nucleon crisis.
Yeah, that's right. Yeah, this is correct. So once again, I don't know enough about quantum chromodynamics to really comment, but it is my impression that they're still struggling with it.